Good evening, ladies and gentlemen, boys and girls. Welcome to Lecture 6 of Topic 1 of Unit 4, Force on a Moving Charge. We're going to be covering the main ideas of Chapter 7.4 of Book 2. Please complete this reading before class. Here are your learning intentions and success criteria. Please pause the video and attempt to complete the knowledge and skills table down here on the bottom right. Okay. So, having a look here, we can see that we are after being able to explain a moving charge in a magnetic field and calculate force and direction. So, in terms of our knowledge, well, we need to know, well, what does a magnetic field do to a charge? Because if we don't know what it does, we can't explain it. Secondly, well, what is this right-hand rule that I'm mentioning down here under my determine criteria? Because you've got to work out direction, like we have with our other magnetic stuff. And our skills are going to be calculating force and how do you actually use this. So, let's talk about moving charges. If we place an electrically charged object, proton, electron, anything like that, next to a conducting wire, so a wire that has electricity going through it, nothing happens. There is a weak gravitational pull, but it's going to be pretty close to zero, so let's just pretend it doesn't exist. The wire has a net balance of protons and electrons. We can see for every proton in the wire there is an electron for the wire, and so the net electrostatic force between the wire and the charge should be zero. Yes, the electrons will pull, but the protons will also push. But as soon as we start to move the charge, this sort of situation, something weird happens. We end up seeing a push or a pull. What we mean by this is either the charge arcs away from the wire or the charge arcs down towards the wire. It basically turns a corner. If we've got a change of direction, because here we're just going left to right, but then we end up, instead of going left to right, we go turning. We have a change in direction, we must have a force. But what's the force? It's not gravity. Gravity can't push. It doesn't seem to be electrostatic because the charge density is neutral and moving shouldn't matter. And those of you who did special relativity with me last year might go, I remember some of this from when we did special relativity and magnetism. But that's not needed for this year because special relativity is part of your last year syllabus, not the year 4 syllabus, not the unit 4 syllabus. But what's this force acting on it? Now, this was originally discovered. It wasn't discovered using this. It was discovered using what's called a cathode ray tube. Basically, it's a beam of electrons coming off of a piece of metal and shooting it through a magnetic field. Kind of looks like this. If you have a really old style TV, one with a big butt on the back of it, and it's very heavy towards the front, but light where the screen is, but lighter towards the back, that has a cathode ray gun in the back of it. If you ever get hold of an old TV and you want to take it apart, it's worthwhile having a look, just be careful. And they found a few things. If they change how strong the magnets are, you get more force, it curves it more. If they shot the electrons faster, in this case they used a faster current, they used a bigger current to have more electrons with more speed, they saw that it also curved more, so force was proportional to V. And also the size of the charge made an effect. Once they started being able to go, well, we'll keep the same size particle, but we'll add more charge to it. So doing some tests with protons and positively charged particles. So the more charge, the more the force. And it leads to a formula. We take all these things, we can see that force is proportional to V, to Q, to B, and we end up with this. The only thing that we didn't mention there was the angle. And this is a fairly straightforward equation. We have the force on a charged particle is equal to, in a magnetic field, is equal to the magnitude of the charge, Q, times the velocity, V, times the strength of the field, B, and the angle between the field and the movement of the particle, which is kind of important. So for example, if the field is going up the here, and V is going right to left across the left to right across the screen, then theta would be 90 degrees. If this was moving up and this was moving up here at a very shallow angle, the angle is going to be something like 30 or so degrees, and so the force would end up being less. So this thing happens when it's predominantly at right angles, or the biggest effect is when it's at right angles. Now, before we use this, we are going to look at another formula, because there's a lot of similarities here, so we may as well see both together. But what this means is that if you have a moving particle, it must respond to magnetic fields, and for it to respond to a magnetic field, it has to be magnetic, which means it has to have its own magnetic field. Moving charged particles create a magnetic field, okay? And that interacts with other fields, such as with wires. Okay. Speaking of wires, let's have a look at it. So if we think about what a wire is, well, a wire is just a set of moving charges. And this formula, this proof here helps us work with that. You don't need to memorize this proof, but I find it a good way to sort of understand the connection between these formulas. Here's the formula we just established. Now, velocity, as we learned in Year 10 and for Unit 1, is displacement over time. The displacement in this case is the length of the wire in the magnetic field. So let's make that substitution. But here we have a Q over T, which in Unit 3 we defined as being equal to current. So now Q over T equals I, and we make that replacement, and then rearrange it because alphabetical order, and we get that F equals BIL sine theta. It may help you to sort of keep it in mind of having the L at the end, the B at the end, or perhaps the I and then the L then the B, just so that you will see some similarities in a second. So going through this formula, we have the gain force will be in newtons, B is still magnetic field in Tesla, I is current in amperes, remember it has to be amperes, and length must be in meters. If you end up with centimeters, convert it. And then theta again is the angle between the wire, or the current, because the current runs the same direction as the wire, and the magnetic field. So field is going up again, current going left to right, or length going left to right, then we'd have a sine of 90 in dealing with the maximum and other things for other angles. Now let's talk about directions. With magnetic fields, with solenoids, and when we were talking about round wires, we used a hand rule, where the thumb was either the direction of the current, and then the fingers were the magnetic curl, or in case of solenoids, the fingers were the curl of the wire, and the thumb told us the direction of the north and the south pole for the solenoid. So we're going to use a hand rule, okay? Because again, this is going to be a 3D situation. Now, Walding uses this image, and I've taken this one and just added a little bit here. That this works, so you have force on the thumb, magnetic field is B, and then the current, or the velocity, okay, because they're both involving movements of stuff, will be along that middle finger. I don't like that. Every other textbook I have uses a right-hand rule. Most of the videos I see online use a right-hand rule, and I prefer the right hand because there is a sort of bit risque mnemonic way of remembering what's what. So the way I remember it is that, let's take our hand and do this with me. So hold your hand up in space, you've got the picture there, thumb up, first finger out, middle finger going pointing to the left. The middle finger is the finger you use to flip somebody off. So that's what we're going to put F on. Okay, F goes on your F finger. Now, the motion, if you're going hitchhiking, don't go hitchhiking when you're a minor, but when you're going hitchhiking as an adult, if we're trying to tell someone we want to lift, we use our thumb. We hook it out, we go this way. Okay? So our thumb is going to be our movement. Velocity is movement. Current is moving electrons. So motion, whether it's V or I, will go on the thumb. And that leaves B along the first finger. Okay? We can approach it using the first formula. Q here is just a magnitude thing, so it doesn't matter. V though, well, that's our first bit, so that's going to go on the thumb. B is our second thing, so we're going to put on the first finger. And then F, the result, must be on the final finger there. The other formula doesn't work for that because you've got BIL sine theta. So if you rearrange this, you can see, oh yeah, let's put B there, and then depending on whether you consider I as the vector or L as the vector, it doesn't really matter in this case. But going, well, yeah, L comes first or I comes first, goes on the thumb, then B goes on the next, and so force will be on the result. I kind of find that the mnemonic with using your right hand and sort of making rude gestures with it does make it a little bit easier. Okay. Speaking of which, I need to label my fingers for when we do the worked examples, because I can't remember the left hand rule very well since I use the right hand rule all the time. Now, here's the keep in mind thing, and I'll try to remember to do some of these with the examples. The directions are for a positive charge and conventional current. So if you think about your circuits, where you have your battery signal with your long line and your short line, you might have a positive and negative written on it. We are dealing with current flowing from the positive terminal to the negative terminal. If you deal with a negative charge, after you do the right hand rule, you have to flip it the other way. Okay? Or when you're dealing with a electron current, where the electrons are actually going from the negative to the positive, thank you Benjamin Franklin, okay, then the force will end up being in the opposite direction if you use the electron current for the direction of your thumb there. Alright, so let's have a look at some examples. First example here, now there is a small typo where it's got 1 times 10 to the 1. This should be 1 times 10 to the negative 5, because this is microcoulombs, and if you look at the work example underneath, he does use microcoulombs 10 to the negative 6 as his value here. So we've got a charge, and it is moving at a speed of 250 meters per second in a field of 1.5 Tesla. Give your answer to 2 sig figs. So just looking at the picture, you can see the field is going up, and the velocity of the charge is moving left to right. Okay. Just get this out of the way. Okay, so this was 7.4a. Now, I will redraw this. Our B field is that way, and our particle is moving that way. So let's start off with the math bit first. We're trying to work out force. And as we saw from our equation, force on a charge carrying particle, QVB sine theta. So let's identify our things. According to the question, Q was 10 times 10 to the negative 6. Our velocity was 250, I believe. Yes, 250 meters per second. That should be coulombs. And our magnetic field was 1.5 Tesla. Now the angle here, they haven't labelled the angle, so you have to go infer from it, oh, it is 90 degrees. Actually at the bottom of the worked example it does say do it for 90 degrees, but I have a feeling that QCAA won't necessarily tell you that it's going to be at 90 degrees. They might just give you a simple diagram like this, or expect you to assume that it's going to be at 90 degrees. Okay, if there's very little information provided about the angle, go with the 90. Okay, now we just sub it into our equation. F equals 10 times 10 to the negative 6 times 250 times 1.5 times the sine of 90, which will just equal 1, and we end up with an answer of 3.8 times 10 to the negative 3 newtons. Now, what about the direction? I'm going to do both. I'm going to do Walding's with the left-hand rule, and I'm going to do my right-hand rule. So, here we have B, so I've labelled my finger here. My finger is going to be B, my velocity going to the side, and so my thumb here is coming up out of the page. Now, do not write up, because up could mean up the page. The correct ones you should be using is out or in. If you wanted to be sneaky about it, you could maybe do the symbol instead. Okay, because remember, out, the tip of the arrow is the dot coming out of the page. That one might slip by some people. I'd recommend writing out. Let's check the directions with the right-hand rule. Okay, so B, again, is still here. Hitchhiking thumb, going to the left. Yep, F is coming out of the page. Let's have a look at the other one. Here we have our same values, but theta equals 60 degrees. I'll draw this as well. I'll try to draw this one a bit larger. Here's our B. here is our V, and this is making an angle of 60 degrees here. So we're going to do the same thing. Let's just do the math first. F equals 10 times 10 to the negative 6, 250, 1.5 sine of 60. Plug it in, and we will get an answer of 3.2. That should be 3.3. 3.3 times 10 to the negative 3 newtons. Now, how do we do the direction here? Because we don't have right angles. I mean, okay, I've got my B running up, but do I have to twist this? Like, I can't. How do I twist that around? What we're doing here, if you've done cross products in specialist math, because I assume it's going to be in specialist, definitely wouldn't be in methods. You've done dot products, which are like looking at the projection of one onto the other. In terms of the cross product, you're looking for how much these things are perpendicular to each other. And so this one here, yeah, this is 60 degrees, but what we're going to do is just rotate it out to 90 degrees for working out our direction. We've already taken into consider the strength of it by taking the sine of the angle. And so in order to do your directions, rotate it out to 90 degrees. If you rotated it to parallel with it, whether going up and down or the other way, the answer would be 0, because if sine of 0 is 0 and sine of 180 is 0, so you can't rotate it that way. If we're going to get a number and we're actually going to get a force happening, then we have to rotate it out to 90 degrees for you to do your finger gun. Okay, so let's do this now with the same thing, because we've got B, we've got that, we've got the force. Okay, so it's coming out. Do the other way. B, finger, force. Okay. Newtons out. Okay, so that's the hardest part, really, that you've got to think about how do you twist it out. Just twist it out to 90. That's all you've got to deal with. I won't turn off the light here, because we've just got the next example on the next page. Okay, now we've got a wire instead of a charged particle. Going to be very similar ideas. We have here two very different pictures, though. A current flows in a wire of length 1.5 meters. It's 3 amps. It's going at 5 times 10 to the negative 5 Tesla. What's the magnitude and direction of the force? And we have here an angle of 55 degrees. And here we can have a more interesting picture. We're told it's 90 degrees, but you wouldn't necessarily be told that, so I will draw it and interpret it for you. Oh, I almost forgot, just as a side note, let's say instead of Q being positive 10, we made this a negative 10. Well, if we do this, we go force, velocity, magnetic field, velocity, force, well, that's positive charge. So if Q is equal to negative 10, it would be then into the page. We just flip the force. Okay? And you do that for anything. If you work out for a negative charge that, it's feeling a force, so if I do like this, if it's feeling a force down into the page, okay, and the magnetic field is that way, okay, yep, that way, that's my thing. So, yeah, root finger, that's my force, that's my, magnetic field going up the page. Oh, velocity must be going that way, but it's a negative, flip it round the other way, which matches the picture there. Okay? With magnetic field, works the same way. Let's see. If force is going... I'm going to twist my arm around this one. If force is going down... I'm trying to do this and not block the camera too much. If force is going into the page and velocity is going off to that direction, this really hurts. Magnetic field will be pointing down the page, but it's a negative charge. We flip the magnetic field around the other way. Okay, so a little bit of practice with that will help you wrap your head around it, and all you've got to do is just swap the direction whenever you have a negative. So 7.4b. Just scroll down so I actually see the numbers. Here we go. Let's draw a picture. We have a field, and our current is forming an angle at 55 degrees. You might go, well, why don't we use this angle instead? Why are we using the small angle, not the big angle? Because we're dealing with sine, and if we were to look at a quick just sketch here, if you're dealing at say 30, or you're dealing at 100 over here, which is going to be 150, the heights will be the same. Alright, so because they're going to be 30 and 150 will be supplementary angles to each other, the y coordinate, the sine value, because if you've done your stuff with unit circles, sine works out the y value, the up and down value, will be the same for either of those angles. Okay, so it doesn't matter which you do, your calculator will give you the same number. Test it if you don't believe me. So, we're working out the force on a current carrying wire, so F equals BIL sine theta equals, well, B, we are told in this case, is 5 times 10 to the negative 5 times our current of 3 amperes, a length of 1.5 meters, and our angle of sine 55. We plug it into our computer and we end up with 1.8 times 10 to the negative 4 newtons. Now, what direction is it? Again, I'm going to rotate my eye out to be at 90 degrees. So now let's go back to the fingers. I'll do with the left hand first. B going up the page. I is going that way, so force must be in. Let's check with the other hand. B going up the page, I going that way, force again is into the page. So I'm going to say 1.8 times 10 to the 4 in. If you wanted to be cheeky, you could do it like this as well. Again, I would not recommend it though. Let's do it with this other situation we have here we have our magnetic field is going into the page. That's our B field, and our current is running down the page. We have the same numbers, okay, so, but in this case, because we have something going in and something coming straight down, they must be at 90 degrees to each other, so the only difference here is that theta equals 90. So now our force will be equal to 5 times 10 to the negative 5 times 3 times 1.5 times the sine of 90, which will just equal 1. So we should get a slightly larger number, and we did 2.25 times 10 to the negative 4 newtons. Now again, let's work out the direction. So B goes into the page, I going down the page, and then so F must be going to the right. Check with the other hand. B going into the page, hitchhiking down, and so that must be our force, our middle finger, going again to the right. Okay. So you can see that really the hardest part of these two formulas is just twisting your arm around until you get the right direction for your right hand rule or your left hand rule. I mean, if you're comfortable using the left hand rule, there's certainly no penalising for it. So you do what you feel you need to do. So last thing I want to talk about is just motors for a second, because this is a very interesting application of the theory. It's not in the syllabus, but you could see the context for it. So here's a basic premise. This is a simple electric motor. We have a magnetic field going from the north to south pole. You can see that with a B. We have a current carrying loop of wire. So you can see it leaves here the positive terminal at the X, comes up, goes through the field, parallel to the field, perpendicular to the field, parallel to the field, and then that bit at the end there is out of the field. And so if we have a magnetic field and we have a current, we must have some sort of rotational force, but we must have some sort of force being applied. And so, B field, current, force, and then over here, B field, current, force. You can see here on this side it's pushing out of the page, and this side it's pushing into the page. And that rotational force makes it turn. This split here means that after it turns around, this side is no longer the outside, it becomes the inside, so that the motion keeps going. this would not be an impossible situation where you'd have to work out the force acting on it. In terms of explaining it, not as likely, but you could be asked to explain, the core idea that's happening in terms of the torque, or the force being applied because there's a magnetic field and there's a current carrying a wire. So this one's a very common sort of situation. So, in this video, we've looked at the following. We've seen how a moving charge interacts with magnetic fields. We've calculated the force on a moving charge in a field, and we've calculated the force on a conducting wire in a field. For your entrance slip to class, please complete questions 1 to 6 in Chapter 7.4, and then copy your answers into the 4.1.6 space on eLearn. Thanks for listening, guys. Have a great evening. Bye.